While people trickle in. Yeah, do you want to elaborate on the seminar we have on Sunday?
Yeah, next Sunday, we're gonna have another one of those. This Sunday, sorry. We're gonna have another one of those seminar meetings with Jake, I think. Not sure if he's on board with that, but
He is after
yeah.
this.
I think it'll be something embedded hardware adjacent. So if you're interested in that, pull up, but yeah.
Sweet. All right. Here's a meeting flag. This is going to be you in approximately 40 minutes once you start working on the challenges. Really just living that ECE stereotype life. Quick show of hands while you guys are punching this in. Who here has like seen the slides, was at, or like did challenges from Pwn 1 and Pwn 2, this being Pwn 3? Show of hands. Okay, cool. It's not a hard requirement. We're gonna go over sort of the idea behind return-oriented programming and everything. But just want to understand how much context to provide. All right. And these slides will be posted on the Discord and on SIGPwny.com. So if you didn't get this right now, you can, it's also very repetitive. So you can probably, snap a picture or something. Okay, so where do we leave off from Pwn? We've got our different memory regions of our program, right? That are loaded, like it's like kind of our runtime picture of memory. Text is all of our instructions, kind of what you probably think of when you think of code, I guess. Globals, unauthorized globals, and then kind of the stuff we really care about is the stack and the heap. Well, actually, spoiler alert, we're really going to care about text in Pwn 3. But this is kind of what we've been working on up till now, is the stack, and I guess we'll do heap in Pwn 4. But just kind of keep this mental model in mind. So again, we're still in the era of, okay, we need some way to deal with vulnerabilities like buffer overruns and stuff like that. So buffer overflow, there's some local variable on the stack. We call a function like gets, we get 40 bytes into a buffer that's only 32 bytes long. We've got some sort of overflow. That's basically what's going on here. And previously in Pwn 1, we could do things like literally just push shellcode directly onto the stack, and we could execute that. And that was a very powerful primitive. So the idea of using buffer overruns is still essentially the same here, but we're going to show you how and why we can't do what we were doing in Pwn 1 and 2. So again, kind of a prototypical example, ret to win. There's a similar challenge like this under Pwn 3 on ctf.sigpwny.com, but we just have some win function,
Wait, 1 second. Does anyone here know, first of all, or remember from Pwn 1? Like what's wrong with this here? The piece of code on the left. Anyone remember? Yeah.
String of arbitrary length into the buffer.
Yeah, and it will write down the stack. So that's what we'll see on the next slide here.
Yeah. Yeah. So again, you press and hold all over your keyboard. You have this string of A's. They show up nice and colorful in GDB and everything. But again, what comes below buffer are like stuff like the save return address where we're jumping back to, and we can overwrite that. So there are mitigations that we won't really talk about today, like stack canaries and stuff like that, to try and prevent overrunning these locals and kind of tampering with the function frame. But this is the general idea. So again, just to kind of show a difference, we have here, this is the buffer. Then we're overflowing not only the buffer, but also the save base pointer and the return address. 4.1 is just A and hex. So then slightly a variation of this technique is that instead of just returning to a convenient win function that was written for you, most of the time you probably won't have that. So just bring your own. And we can include shellcode as part of our buffer. And then for our return address, we're just jumping to the shellcode we entered as part of our buffer overrun in the first place.
Yeah, also, just to be clear, the shellcode doesn't have to be at the buffer. It can be anywhere in the program. It can even be after this, like address of buff, after the return address. You can put it if you don't have enough space or something like that. So yeah.
Yeah. Okay, so essentially, people were tired of their program. People were tired of getting pulled out. Like, all right, that's it. Enough of this nonsense. Someone had the bright idea to be like, you know what? It's probably not such a good thing that people can write shellcode on the stack. So we're gonna say, all right, if it's on the stack, we're gonna say like if you can write to it, you can't also execute it. We're not actually gonna like let you write your own exploits basically. So this is pretty sensible. So the idea, you'll see this written as like, you know, write XOR execute, right? You can either write to something or you can execute from it, but you can't do both. So this stores the attacks we just showed, or not the read to win function, but the read to shellcode function. So, you know, what are we going to do? And by the way, you can check if a binary has this enabled using checksec. This is also in like Pwn tools and everything. So how can we get around this? Does anyone have any ideas before I kind of reveal the answer? I'll give you a hint. The answer is in the slide title. Yeah. You can mitigate that. That's true. You can mitigate it. Like that's technically the truth. Yeah. Any additional, that was pretty insightful, but any like, you know,
You like just write disable NX. Is that possible?
disable NX.
Okay, it is actually, but not what we're going for, but there is a function that you can change the permissions of certain areas in your address space, which not what we'll get into, but that's a very good thought.
Yeah. Assuming we couldn't do that. So again, we can't execute stuff on the stack. But what's a place that's always getting executed? It's just part of normal program execution. It's like the code, right? Like just like the original program. So basically the idea here, and what I really want to hammer home is that return-oriented programming is kind of one, I guess probably the simplest form of what's a broader class of techniques or attacks known as code reuse attacks. So they're being like, okay, I don't need to bring my own shell code. I can just reuse whatever code is already in the program. So again, we're talking about return-oriented programming. Don't worry about the return bit of this currently. Akhil will give a very nice demonstration in just a second. But the idea here is we are going to find kind of a series of small little nibbles. Not nibble. That word is overloaded in computer science. Small. We won't go with chunk either. Small gadgets. Oh, perfect. Small gadgets of instructions that we can jump to and we can execute, and we don't have to worry about kind of what's going on around them because we can then ret out and you don't have to continue executing. And we can chain these little gadgets together to essentially get arbitrary computation. It's effectively Turing complete. So this is the idea. We're reusing code that's already within the program. One of the cool things is that this isn't just like we're reusing like the win function that the challenge author conveniently included for us to print the flag, but we can just reuse arbitrary bytes that are in the text section or anywhere that's marked executable. So this is a pretty interesting technique. So what does this actually look like?
Yeah, so yeah, enough talking about ROP. Let's get those brains working, let's do some ROP ourselves, all right? So you have these 4 gadgets at a high level. This is not what they actually look like in code, obviously, but you have these 4 gadgets. We want some way to end with B being equal to 3. Does anyone know how to like order these gadgets? You can use one multiple times, but is there any ordering of these gadgets you guys can think of that will end with B equals 3? Yeah. Yeah.
Just a question. Are there preset gadgets on every program that's compiled, or do you kind of poke around within that?
We'll get to that, but
Great question.
yeah, that's a very good question. But yeah, that was correct. You do gadget 2, set A equal to 0, then you can increment A 3 times with gadget 1, and then gadget 3 will set B equal to A, so then B will end up as 3. All right. Oh, yeah. Okay, and okay, now slightly less high level. This is kind of what gadgets actually look like in code. You can identify them because they end with a ret instruction. Ignore that for now. It has to do with why you can even change them together in the first place. But so can anyone find an ordering of these gadgets to set RBX equal to 3? RBX is a register, by the way.
Can you guys see the, okay. So make sure the hint text on the left is big
Right.
enough. Any takers? We heard from you, but anyone else, out of curiosity? Okay, I'll bite.
So you start with gadget 2 to put on RBX. And then I would swap RX, RBX with gadget 1. And use gadget 3 times and swap the gadget.
Yeah, that's absolutely correct. So yeah, you will call gadget 2, set RBX is 0, then you can swap them with gadget 1 and increment RX 3 times, and then swap them back, and RBX is equal to 3. And so these are kind of a bit contrived. Obviously, the Pwn challenges will not have you setting random registers. Actually, first one kind of does, but that like most of the time you'll be trying to do something a little bit more like intentional, you know, like not contrived.
Or just like a quick pause here. If you kind of like take your finger, or maybe you have multiple fingers, you have 4 fingers, hopefully most of you do, and you kind of block out the ret, right? And you chain these, you organize them like Legos, and we can say use multiple Legos together. Hopefully this looks just like an ordinary assembly program you guys that you may or may not be used to. But if you're not used to it, it's okay, because you become used to it with these building blocks. It's like Duplo. I don't know what the analogy of Lego would then be, but I don't know. Everyone kind of on the same page here of these are our primitives, with which instead of using shellcode, we're kind of like reusing existing code. Okay, cool.
All right, so before with ret2win or ret2 shellcode, we would just overwrite the return address with like a single address that will take us to wherever we want to go, and after that, like we'd pwn the program. But here we can actually put multiple addresses one after another, and assuming each gadget ends with ret, which it should, it will, after a gadget is finished, it will return to the next gadget on the stack. The specifics of why that works has to do with the actual calling conventions, how the stack pointer and the instruction pointer like kind of work together. Like a ret is basically like the same thing essentially as a pop RIP. So it will pop the next thing off the stack into an instruction pointer. In this case, the next thing off the stack would be gadget 2. So, and gadget 3 and so on. So yeah, here's an example. This is sort of like more realistic in what you do with ROP. Like for instance, let's say you have a win function, but this time the win function takes a parameter. So you won't be able to print the flag unless A is equal to that number. So what you can do is before jumping to win, first you can jump to a pop RDI gadget. What that does is it will pop a value off the stack into the RDI register, which is based on the calling convention, is the first argument for a function in x86-64 at least. Different architectures have different calling conventions, but yeah, in x86-64, RDI is the register that holds the first argument. So with a pop RDI gadget, we can pop that next value on the stack, which is the number. We can pop that into RDI, and then when the ret or at the ret instruction, the address of win will be popped into the instruction pointer, meaning that after the pop RDI instruction or gadget is done, the next place that the program will go is the win function with RDI being set to the correct value. Does anyone have any questions about that? That's kind of like involved. We're good? Okay. So yeah, for ROP in practice, there's usually no win function. Like you're not going to have a win function, even if it accepts a parameter. That's usually like probably not a thing. So most of the time what we want to do is we want to pop a shell, or basically like run bin sh on like the computer that's running the program. So that you're pwning. So the way we can do this is one is we can just like do a syscall. So like execve is a syscall. And we can, if we set the 3 registers, like the first one to point to a string, bin sh, and the other ones you can just set to null, this will actually just pop a shell. So if we can, that's actually what you need to do for one of the ROP challenges. So yeah, and or if you have libc, which we'll talk, or like a libc leak, and you know the address of system in libc, which we'll talk about in a bit, you can just call system bin sh, and that will also pop a shell. And so yeah, those are 2 of the more common ways you will like, I guess, the goal of your exploit in a pwn challenge or in a ROP challenge. And yeah, so you might think, how are we going to find this gadget? So I think it's similar to a question you had before, like where are they stored? Like, so like every program, basically every piece of like of a program that ends with a ret is technically a gadget. So like you can chain them together. So obviously your program will have them. Every function ends with a ret or a leave ret. But depending on how like big your program is, there won't be that many. There might not be that many. So like the first way you can do this is you can just look through the program yourself. You can either just straight up open the assembly and like just look, which is the most fun way, right? And then maybe for Juniper, right? Okay.
It builds character.
But or you can make it slightly easy on yourself by grepping for rets and then like getting 5 instructions before that ret to just see any gadgets you can find. Then if you want to make it even easier, you can use tools that already exist like ROP gadget, which is a good one. It will just print all the gadgets in the binary, or you can even actually just have it generate a ROP chain yourself. So you can try that on one of our challenges or multiple, I don't know, but and it'll actually generate a ROP chain for you that you can use to exploit the program, which makes it like too easy, I think. So don't do that. But I mean, do that in competitions. Maybe don't do that for the challenges because that'll make it too easy. But then other than that, Pwn Tools has good ROP utilities. So you don't actually have to like look for the address. Like Pwn Tools has a function like find gadget, and then you could just put the gadget that you're looking for. And if there's an address that is that gadget, then it would just give it to you. And Pwn Debug can also, which is like an extension to GDB, can also help you find ROP gadgets. The last thing I want to talk about briefly is a one gadget. A one gadget is like one gadget that pops a shell. So like it's basically a win function, honestly. You just call it, go to that gadget and like then you have a shell. So you can there's a tool called one gadget that will help you find those. A lot of times those they definitely won't be in your program. Usually they'll be in libc, which we'll talk about in a sec. But yeah. And are you talking about libc?
No, you're talking about libc.
Oh, okay. So yeah, now we're talking about libc. So most of the time, your binary obviously is not going to have like a bunch of gadgets. Like if you like most of our challenges are like 1 file, C files, like maybe 2 functions. There's not going to be that much. So it's going to be hard to actually build like ROP chains or like call syscall, for example. Most programs probably won't actually have a syscall, but like anyways, so in libc, however, there's like so many gadgets, like almost like there's basically you can find anything in there. Like this is from ROP gadget. I just ran it on a version of libc, and it said there was 100,000 gadgets in there. Like there's plenty of stuff to work with. So it's like, so libc is usually, if the program is dynamically linked, it'll be linked near the top of memory, just under the stack. So like you can use a lot of libc functions to construct your ROP chains. And so a lot of times though, because of ASLR, which I think George will talk about in a bit, you don't actually know the address, like the absolute address of like a gadget in libc, because like memory segments are randomized with ASLR. You don't know exactly what the address is. So often the goal of the steps a lot of times in Pwn challenges are to first leak a libc address, and then like once you have a libc address, you can calculate offsets to anything in libc from that address, and then you know where all the gadgets are, and you can ROP with those libc gadgets. So yeah.
Cool. All right, just checking in. How are we doing so far in the ROP? I see some faces that are like, yes, I'm ready to go. They're already solving challenges. I see some people who are like, what is a ROP? You know, I came here because I saw things about sleighs and there's no sleigh, you know. We feeling okay about ROP? You guys are ROPers? Yeah. Thumbs up from the ROPers. Yeah. Okay. So okay, so we have the slide about ROP mitigations, but actually, as it turns out, this concept of code reuse is a very, very, very powerful technique. So honestly, if you're going to take away anything from all of the Pwn meetings, it's probably be ROP. I'll kind of go into like how this is being mitigated nowadays, but it's very, very, very powerful. So the two things that kind of go hand in hand are this idea of position independent executables and address space layout randomization. So, you know, before, I guess I'll just go back a few slides just to get an idea here. When we're on the stack here and we're kind of crafting our exploit, you know, we are overrunning some buffer, and then we're putting on the stack an address of a gadget we want to go to, right? But with these mitigations, every single time the program is run, the base address is changed essentially. So we don't know an exact offset because if we're jumping somewhere, we need to know like, you know, address OX blank, 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 blank. So again, we're actually, this isn't like that bad because we still know the relative offsets. So there's some things like, I think like fine-grained ASLR, but you don't have to worry about that for most challenges. The idea here just being, you need to find a leak to some address that you know. And as long as you, okay, I know the address of A, and I know that the address of my gadget relative to A is, you know, OX something, something, something. And now I can, you know, take that, and now I have the address of my gadget. So that's how you beat ASLR. Again, so this does require a leak, but, you know, again, like the ROP itself is not, like, it is not a mitigation against ROP by itself. This is more just like a hampering your progress.
Yeah. Also, there's a way to get an ASLR leak or a pi leak, for that matter, with ROP too. If I mean, obviously you need the like addresses of the gadgets to do that with. But like, assuming you have those, like ROP is so powerful that you can even beat the ROP mitigations. You know, so you should learn it.
Yeah. So this is an example. I'm mainly going to go over some of the kind of gotcha stuff, but I would highly encourage you, if you install Pwn tools, I think either through your system package manager or Python, it comes with like a little command line utility, which has like a template option, which will populate a Python file with like the latest and greatest, you know, template solve script for Pwn.
Also, for the first Pwn challenge, I wrote a template for the first ROP one. Not the ROP gadget one, like the ROP one, whatever it's called. Yeah, I have it.
RET2 win V2.
Yeah, that one. Yeah, I have a template in there, so you can use that as well.
Yeah, so there are a few things that are a little different from, I guess, like a traditional Pwn tools template. The main thing being, again, we have our exe, libc, which most of the time it will need. If you find a leak at some point in, you know, some other input output from the program earlier in the exploit. The main thing that's kind of relevant to ROP here are these gadgets. So here we're using Pwn tools like ROP submodule or library to find the gadgets for us, which is, you know, very, very convenient. I would potentially recommend trying to, like, you probably don't have to go through like the binary objump yourself, but even if you just run ROP gadget manually, which this is just using under the hood, to kind of find, oh, you know, what gadgets am I looking for? What do I need? Oh, I need, you know, I need to pass an argument. I need to bring something into RDI, right? Oh, and it's an address XYZ. And if there's ASLR, you know, I need to find an offset relative to that, but that's the general idea. So you have your gadgets. In this case, you have a system from libc, and then when you're crafting your payload, this is similar to Pwn 1, I think, not Pwn 2, I think just Pwn 1, where you want to overflow a certain number of bytes. There's also a tool in Pwn tools you can use called like a cyclic, which is helpful for that. You know, you have your fixed offset, and then you just chain them together. So, you know, This is for stack alignment, which is important for libc, but I don't think for anything else.
Yeah, you might encounter that in one of the challenges. So, yeah, just remember that you can fix that just by adding a ret like to the beginning or right before your function at last gadget in your ROP chain.
Yeah. And again, we have this address. So if you kind of like mentally map out what we're doing in program execution, we've like we've popped the address. We've popped and jumped to the address of this pop RDI gadget. And now the next thing on the stack is our bin sh string. And now again, the gadget is just doing pop RDI. Now let's pop that from the stack into the RDI register. Then we return. We're back here at system. We go to system, and Bob's your uncle. You're good. You have shell. Any questions about this? Don't be too concerned about the specifics. The main idea is really just, here are my gadgets. I'm stringing the gadgets together. You kind of guess and check this number. Yeah.
Oh, I guess it's not in this screenshot, but yeah, it would be like the address of a string that's in sh.
Yeah,
that points in sh. Yeah.
So the idea being here, I think we had this a few slides ago. Like you just want to do like system bin sh, and in order to pass the string bin sh to system, you'll pass it an RDI if you're on x86, 64. There's another thing, like, again, the technique of ROP is architecture agnostic. How you pass arguments to functions, you'll, I guess, kind of have to worry about it for ROP. But the idea being, like, you have to just read the docs, basically. x86 is a little bit wonky. Yeah, so again, to kind of hammer home the point of how powerful this is, the original ROP paper, it's like 2007, I think. Justin Bieber was super popular. Some of you may not even been born. I don't know. And then this shadow stack mitigation. The idea being you keep a read-only copy of the stack once you enter a function to make sure you haven't been tampering with things. It's kind of like a stack canary, but a little bit more secure. This got merged into Linux in 2023. So like ROP was just like completely unchecked for like over a decade. And even then, shadow stack, this like requires hardware support. You can't basically fix this in software. There are certain other things you can do. You can try to compile programs to not add these gadgets, but that's kind of a fool's errand, honestly. So it's very powerful. Also, I kind of briefly wanted to touch on that. There's other similar concepts. There's like SIG return oriented programming, where it's the same concept, except now you're kind of like changing the context after you call out to a signal handler, change all the registers. There's other kind of variations, but it's just like once you've eaten ice cream, you like ice cream, you can move on to raspberry and chocolate and vanilla and whatever after that. But yeah. So again, to recap, Akhil already went over a lot of these resources, but your bread and butter, Pwn tools as always, Pwn debug. Again, you can use GDB, you can use Jeff, you can use Pwn debug, all of them are good. ROP gadget, which again, this has an interface in Pwn tools and Pwn debug already. One gadget, libc database search. This is kind of important. When you're doing, I guess, calling out to anything in libc, I don't know what version of libc you're actually using. So it's pretty common in challenges that like the author will just give you the shared object file of libc. But if not, there are ways to kind of determine which version of libc you're in based on offsets and stuff like that. And then when you're all done with the ROP challenges we have prepared for you, there's a very, very good resource called ROP Emporium, which I guess I kind of liken. It's like Nightmare, but instead of for Rev, it's for Pwn or for ROP. Yeah.
Nightmare has ROP too.
Nightmare also has ROP. Oh, that's
I
crazy.
think so. Or I don't know, actually, never mind.
I haven't done Nightmare in like a while, so this analogy is probably dated. Anyway. Yeah, so that's kind of the long and short of ROP. Any questions? Going once, going twice. We'll be walking around afterwards too. Yep. So next meeting is seminar with Jake, embedded security. That'll be fun. And then next week, Crypto 4, electric cryptography with Sognick and myself. Look forward to that. Cool. Here's the flag. If you have any questions, just let us know.